Good afternoon, class. This is Mr. Precella, and today we're looking at exponential functions. This stuff is going to be important for our discussion on logarithms, which is the next homework assignment, or at least that's logarithm started the next homework assignment. And some of this material you may have seen if you took Math 371 recently. There is some foundations blended into this assignment. So here goes. Exponential functions. I'm going to switch over to mine. We're going to have to recall properties of exponents. And as we run into some that are important, I'll be reminding you of them. When I'm using the lowercase letter b for this discussion over exponential functions, or for the logarithm stuff we're going to be doing, we'll assume that the letter b is a positive number and that it's not equal to 1. Here's the first property that I want to remind you of. It's the zero exponent property. Zero exponent property. The zero exponent property says b to the 0 is defined to equal 1. Any non-zero to 0 power is going to equal 1. And to illustrate, the common mistake is people think something to the non-zero to the 0 is equal to 0. No, that's not the definition. Looking at number 1, we have negative 37. Oh, well, these properties are always true, okay? I mean, they're true even if the zero exponent property is true even if the base is negative. So we have a non-zero to the 0. What does that equal? The number 1. Suppose we had this one. I'm going to make up an example.
Can you switch back?
Oh, thank you. There it is. Negative 37 to 0 is defined to be 1. Here's one I'm going to make up. Let's see what y'all say. Pi to the 0 power. What is that? About 3.14 to the 0? What will that equal? 1. Okay. We're going to be working with some negative exponents in this assignment and the next assignment. So I want to remind you how negative exponents work. These are the negative exponent properties. I'm going to state 2 of them. Negative exponent properties. Okay, b to the negative n power. What do we mean by a negative exponent? You can't say, well, x cubed is x times x times x. A negative number is not a counting number. So you can't, we can't think of negative exponents as just repeated multiplication. A negative exponent is another way of expressing a reciprocal. You can write base to a negative exponent as 1 over, then it's just the base to the positive exponent. That negative exponent that's on the base means you're looking at the reciprocal of the base to the positive power. If you have a fraction, by the way, some terminology, I was just saying it, assuming that y'all remember that. The thing that's being raised to power is called a base. That's why I like to use b's in this case, because it's a base to a power. Suppose our base is a fraction. Suppose we have A over B, all raised to the negative n. If you have a fraction to a negative power, just like the reciprocal of b is 1 over b, here it's saying the reciprocal of a over b. Well, that's b over a. So we take the reciprocal, we flip it, b over a, and then it's to a positive n. That negative exponent says take the reciprocal of the base, that means flip it, and then the exponent changes positive. Let's see if y'all were following that. This is number 2. Let me write it down, and then I'll switch over. 1/6 to the negative 2 power. 1/6 to the negative 2 power. We have a fraction to a negative power. That says take the reciprocal. If you flipped 1 over 6, what would you get? Just 6 over 1, which is the same thing as 6. You change the negative 2 to a positive 2. And we know that 6 squared is equal to 36. Any questions there with our logic? If you have a fraction to a negative exponent, you take the reciprocal of the base. When you flip 1 over 6, you get 6 over 1, which is just 6. Then you change the negative exponent to a positive exponent. Now, that can't stay that easy, can it? That's number 3. This one will be a little messier, I suppose. Let me write it down. 3 over 5 to the negative 4 power. Once again, it's a fraction to a negative exponent. So you take the reciprocal. Flipping 3 over 5, we're going to get 5 over 3. The negative 4 power becomes a positive 4 power. So what's 5/3 times 5/3 times 5/3 times 5/3? You have 5 4s, so that's a 5 to the 4th, all over 3 times 3 times 3 times 3, that's a 3 to the 4th. Ernestina, you have your calculator, so you check me. 5 times 5 times 5 times 5, my mental arithmetic says that that's 625. 3 times 3 times 3 times 3, I'm getting an 81. If my mental arithmetic is correct. Where's my little calculator? 6, okay, you got this. 5 to the 4th is 625. 3 to the 4th is 81. And you want to have your calculator with you as you're doing these problems. Certainly make matters easier.
So you just leave it like that?
Yes. If there were a common factor, I would cancel it. But I know I'm not even going to try to find a common factor because that 625 came from 5 to the 4th. 5 is a prime number. 3 can't divide into 5, so there's no way that fraction can be reduced. Because if we're going to be reduced, then we should be able to cancel something in the form of 5 over 3. 625 81st. 625 over 81. Any questions there? And number 4, let me write it down. A to the negative 9, is that a to the negative 9? Well, this one looks more like the first statement I wrote concerning negative exponents. We just have a single base, it's not a fraction, to a negative power. So, to rewrite that using a positive exponent, a to the negative 9. The negative becomes the 1 over. The base is a. The negative 9 becomes a positive 9. Any questions there?
Okay, so you would put the 9 with the A on it.
That's right, because 1 to the 9th would just still be 1. Okay? Did you follow that? That exponent goes on the denominator. Technically, what's happening is the same thing here. I guess you could say, well, 1 to the 9th, but 1 to the 9th is going to stay 1. 1 to any power is 1. So the exponent's really only being applied to the to the denominator. That's the definition of negative exponent. It goes back to what we wrote right here. A base to a negative power. What do we mean by a negative exponent? You can't count a negative number of times. That negative exponent is saying the reciprocal, 1 over. Just like when it's a fraction to a negative, that negative is saying take the reciprocal of a over b, which is b over a. So that is a 1 over, that's an a, exponent key, positive 9. Any questions there? Let's just go on to number 5, see what it is. Now the instructions say to express using a negative exponent. They've given us something without a negative exponent. They want us to write it using a negative exponent. This is number 5. I think I have room to do it right here. 1 over 9 to the 6th power. One over 9 to the 6th. We're going backwards, taking something with a positive exponent, writing it with the negative exponent. So we drop the 1 over. We're dropping the 1 over. The base is just going to be a 9. But what's going to happen to that 6? It's going to be a negative. That negative is taking the place of the 1 over. That red negative exponent means 1 over. That red, I tried to make it red. Any questions there? Let me type that in. That's 9 to the negative 6. Same instructions here. Express it using a negative exponent. This is number 6. 1 over d cubed. One over d cubed. I tried to make that, well, I messed up and wrote it all black. Well, there. Well, we're going backwards. We have a positive exponent. We want to go back to a negative exponent. So we're going to drop the 1 over. We have a d, but instead of a cube, what exponent are we going to have on it? What's going to take the place of the 1 over? A negative, so the exponent will be a negative 3. For d to the negative 3. I remember working with rational exponents back when we were working with radical equations. I need to remind y'all of some properties involving rational exponents. That means a fractional exponent, not this thing right here. That's what I'm talking about when I say a rational exponent. It's a fractional exponent. I think I'll write it out as fractional exponent properties. Suppose you have an exponent in the fraction. Okay. B to the 1/2 power. That's the same thing as saying the square root of b. I remember after those long involved radical equations towards the end of the assignment, we had a problem where it was quantities raised to the 1/3 power, and once you realized that exponent of 1/3 just meant a cube root. That's an exponent of 1/3 is the same thing as the cube root of b. Oops, the cube root of b. Y'all tell me, b to the 1/4. What sort of a radical will we have there? It won't be a cube root. There will be a 4th root of b. And in general, if you have an exponent of 1 over n, b to the 1 over n, that's defined to be the nth root. Whatever that denominator is there, that's the little thing that you put on the radical. That's called the index. So that's that denominator, if the fraction's in the form 1 over, that denominator is the index of the radical. Rewrite without rational exponents. So we don't want that 1/5 exponent appearing in our answer. This is number 7. Okay, here's number 7. Once you know those properties for fractional exponents, this goes pretty fast. I couldn't hear you.
Is it just 5 square root x?
Well, actually, it's the 5th root, okay? That's common to call it 5 square root, but it's really the 5th root of x. That 1/5 exponent, oh, wait a minute. Oh, where's my brain? That 1/5 exponent is the same thing as the 5th root. So, we don't use this hot button here. That's for square roots. Any other type of radical where you have an index appearing, you have to use the nth root key. Up here where the cursor's flashing, you type the 5. Underneath the radical, you type the x. Any questions there? rewrite without rational exponents, and simplify if possible. I think this one we'll be able to simplify. This is number 8. 81 to the 1/4 power. 81 to the 1/4. That says that 1/4, that's going to be the same thing as the 4th root. Oh, I'm doing it again. I'm just forgetting every time. 81 to the 1/4. That 1/4 exponent is the same thing as a 4th root of 81. And now let's see. Maybe we'll figure this out without needing a calculator. What number can you raise to the 4th power to give you 81? Well, let's see. What number? What number to the 4th power will give us an 81? There it goes. Let's see. What times what times what times what? Any ideas? Well, when you think of 81, I think of 9 times 9, right? Well, 9 times 9, how can you write that as the product of prime numbers? 9's a perfect square. 3, I think 3 to the 4th. 3 raised to the 4th power. Does that give us 81? Yes, it does. The 4th root of 81 is equal to 3. Any questions there? Suppose our fraction is not, suppose the exponent, these properties here have just an assumed numerator of 1, 1/2, 1/3, 1/4, 1 over n. Well, we know that the fractions don't always have a numerator of 1. Suppose let's see, how will I write it? Let's say b to the a over n. If you have an exponent, that's a fraction, and the numerator isn't a 1, that numerator there is going to be the power. We'll see what I mean by that in a moment. That denominator, that's the index on the radical. So you have an nth root, b to the a over n is equal to, it's going to be an nth root of b all raised to the power of a. That denominator says take the nth root of that number. The numerator is the power you raise the stuff to. And it's not that bad. It's not as bad. Probably would have been better if I'd just done number 9 and told you how to do it. Because that looks sort of bad, I must confess. Okay, number 9. We want 16 to the 3/4 power. 16 to the 3/4. What sort of a radical am I going to have? Oh, I forgot to turn on my microphone. Y'all should have said something if you couldn't hear me. I'm sorry about that. No, I forgot to turn it on. You should have said something. Okay, I have a question. I'm going to write now I'm not going to write the radical. Are we going to have a cube root or 4th root? Which one Which one of them determines the type of root? Is it the number on top or the number on bottom? Bottom, so it's going to be a fourth root of 16. We're going to have to simplify the fourth root of 16, and then whatever we get, we're going to have to cube it. The numerator is the power, the denominator is the index. Now the fourth root is 16. What times what times what times what will give you 16? You're thinking to yourself, what to the fourth power will give you 16? Earlier, we saw that 3 to the fourth gave us 81, so 16 I think of as 4 times 4, but 4 is 2 times 2. I think it's 2 to the fourth power. Let's verify that right here. 2 raised to the fourth power. Does that give us 16? Yes, it does. So the fourth root of 16 is 2. We simplify the radical first. The fourth root of 16 is 2. Now what's 2 cubed? 8 for my final answer. Now, if you view an example, they may take the 3. You could put the 3 underneath the radical. You could put the 3 under the radical and then take the fourth root of 16 cubed. The problem is 16 times 16 times 16 is mighty big. You're trying to figure out the fourth root. My recommendation, simplify the radical and then perform the exponentiation. Any questions there? Oh, let's see. Let me come back over here. I don't think I typed in the answer, did I? There it is. We said that was 8. Hopefully there's another one like this. Okay, this is a good one. Number 10. We have 36 to the 5 halves. What sort of a radical are we going to have? A fifth root or a square root? A square root. That denominator says that it's a square root. And remember, if it's a square root, you don't show the index, okay? It's just a square root of 36. And what power are we going to have to raise all that to?
Can you switch back?
Oh, switch, you're right. My goodness. That 2 says that it's a square root. We're going to have to raise all this stuff to what power? The fifth power. I agree. And we know the square root of 36 is...
Wait, isn't, don't you put the 2?
On the radical?
Yeah.
It's standard practice for square roots. If the index is a 2, we don't show it. If the index is a 2, we don't show it in terms of radical notation. So y'all said that's a 6 to the fifth power. Let me dig up my calculator again. Here it is. 6 raised to the fifth power gives 7,776. So 7776. Let's see, 7776. Oh, okay, number 11. Here they want us to rewrite it using rational exponents. That means using a fraction. We're going in the opposite direction. What we've been doing is taking the stuff with the fractional exponent, writing it with radicals, and reducing it if we're able to. Here, they want us to take this radical expression and rewrite it using a fractional exponent. Now, the square root of 3, that'd be the same as 3 to what power? 1/2. A square root is the same thing as the exponent 1/2. So, come over here. That's a 3. Do y'all use the hot button key, or do y'all just do the shift up arrow? I like to use the shift up arrow, and then maybe we should put the little hot button fraction so that a 1 goes there, and underneath it we have the 2. Any questions there? Here's another one we're going to write using a rational exponent. We're not going to write it with a radical. This is number 12. We want the cube root of 23. That's the same thing as 23 to what exponent? 1/3, I agree. (23 to the 1/3 power).
Wait, why is it 1/3?
Go back. There. We're using this property in reverse. A cube root is the same thing as a 1/3 exponent. Just like a square root is the same thing as a 1/2 exponent. So, 23 to the 1/3 power. Any questions there? I want to define what I mean by an exponential function. An exponential expression has an exponential algebraic expression has an exponent that contains a variable. An exponential function move this up. An exponential function has a variable in the exponent position. That's what's different. We're going to be seeing exponents in the variable. Well, we've been working with exponents all semester long, but we haven't seen variables in the exponent. We've seen things like f of x equals x squared. That's a quadratic function. We've had exponents, but there's not a variable there in that exponent. If there are no exponents at all appearing, things like f of x equals 2x, we call that linear because the graph is just a line. But in order for something to be exponential, the thing up there, the exponent, has to contain a variable. It may contain other stuff, but it's got to contain a variable. Here's an example of an exponential function. Instead of x squared, how about 2 to the power x? That's what I mean by exponential. We're going to devote the rest of the class to 2 general topics: graphing exponential functions and solving exponential equations. The graphing is going to be pretty fast. We're not going to do anything real advanced for graphing. We're just going to plot points until we see a pattern. So graphing exponential functions. Let's just look at an example. I think that'll... Oh, and there's no exponential graphing tool built into this assignment, so we're just going to graph them on paper, and then it's a multiple choice. We'll choose the correct graph. But the first thing we'll do, get a graph drawn on paper. And this is y equals 6 to the x. This is number 13. We want to graph y equals 6 to the x power. An exponent can have, can be any number. It can be positive, negative. We've seen that. It can be a fraction. So you can plug any numbers you want to there for x. I wouldn't use something like 5, because 6 to the 5th, that'd be a mighty big number to try to label on the y-axis. Generally, if you use the integers from -2 to +2, that's enough for you to get a good picture of the graph. I'm going to make a table of values. X, Y. I said, if you just use 2, 1, 0, -1, and -2, that should be enough for you to get a good picture. Some of these points you may not want to bother plotting. When you plug in that 2 for x, 6 to the 2nd power, 6 squared, what are you going to get for that y coordinate? You're going to take the 2, plug it in for x, you get 6 squared, which is equal to what? 36. That's one of those points I'm not going to plot. I'm not going to try to count 36 units up. What about 1? 6 to the 1st power. What's that going to give us? Just a 6. Now be careful on this next one. Remember the first thing we did a moment ago when we started this lecture. 6, replace the x with 0. 6 to the 0 power, what is that defined to equal? 1. Good. Oh, where is that? There it is. 6 to the 0, any non-zero to 0 power is defined to equal 1. Now we have to plug in the -1. So be careful. 6 to the -1 power. Remember your negative exponent properties. 6 to the -1. 6 to the -1. That's the same thing as 1 over 6 to the +1. That negative exponent is the same thing as a 1 over. So we're going to have a 1 over 6 to the +1, which is just 1/6. Follow that same logic when you plug in -2. 6 to the -2 power. That's the same thing as 1 over. The negative becomes a 1 over 6 to the 2nd power. We know 6 squared is 36. Look how small these y coordinates are getting. Let's say and go this ordered pair, you go left 1 up a sixth of a unit. Imagine breaking 1 unit into 6 equal little sub intervals, moving up 1/6. Here you're going to go left 2 up 136. Break the interval into, imagine breaking into 36 little equal subintervals and move up one of those. It'd be extremely close to 0. Y'all see the ordered pairs we've created? We have 236. We have 1/6. We have 0, 1. We left 1, so negative 1 up a sixth of a unit. Left 2 up 1/36 of a unit. Well, I have a question. These y values are getting smaller. As the x values get more negative, the y values are getting smaller. Will they ever become negative? Will we ever have a point, an x value, that'll make that y value equal 0 or be negative? No. A positive number to any power will always be positive. Remember, I said that when I started this, I said those bases are going to be positive. A positive number to any power, must be greater than 0. So you don't have to worry you're going to get negative y values. That can't happen. Draw an XY grid. We're going to plot these points to the extent that we're able to. As I said, I'm not even going to bother with that 2, 36. I'm not going to count up 36 units.
Question. Could
Yes.
you just put 2 points? Could you just plot 2 points?
I'm going to plot 3 basically, okay? That'll be my pattern. You don't have to get them all plotted. I'm not going to plot this one because you got to go right to way up 36. I'm off the paper at that point, aren't I? So I'm not going to bother plotting that one. 1/6, right 1, 1, 2, 3, 4, there it is. Right 1 up 6. Left, right, 0. We were able to plot this one. We didn't bother plotting that one. Left, right, 0, up 1. I'll definitely plot that point. Negative 1, up 1/6 of a unit. Here's negative 1 on the x-axis. Imagine breaking this little interval that I'm pointing at, that one little interval, break it into 6 little subintervals and move up 1/6 of that. So left 1, up 1/6. To the naked eye, it probably looks like you're touching, that it's touching the x-axis. But it isn't, because if it touches the x-axis, you'd have a y-coordinate of 0. Can the graph pass below the x-axis? Are we going to have anything out here? No, because that would mean the y value has to be negative. At left 2, you only go up 1/36. That's even closer to the x-axis. To the naked eye, it would look like it's sitting on the x-axis, but there's always a little distance between the curve and the actual graph. Now, to the naked eye, it looks like that curve is sitting on top of the x-axis, but there's always a tiny little bit of space. In general, for exponential functions, you should expect one side. Think about 236. If we plotted that, there's 2. 36 would be somewhere way up here. So the right side in this case is extremely steep. You should expect one side of the graph to be extremely steep, almost vertical. The other side, very flat, almost horizontal. You hear about exponential growth. Population growth is exponential. That's what is happening. We're now at that unfortunate point in the history of this planet. Our population is growing at real vertical, extremely fast. During my lifetime, we went from 3 billion to 4 billion to 5 billion to 6 billion to 7 billion. Have we hit 8 billion on the planet? I think so. I think so. So that's what they mean by exponential growth. Population growth is exponential. You pass a point where it just starts skyrocketing. And that's what's happening now. And I guess Mother Nature is sort of fighting back against that with viruses and tsunamis and natural disasters. But enough of that. Let's see. Let's just be grateful we don't have to use a graphing tool to graph this, but it's just multiple choice. Let's get over here. I can't get my mouse to work. Oh, let me move this thing. A, B, C, or D? Which one? Well, it's clearly not A. That's a line. B? What do y'all think? That looks like it. C? No, it's not a parabola, but it's maybe a y equals x to the fourth or something. And D? No, the only one that comes close is response B. Any questions there? You should expect one side to be extremely flat, almost horizontal. The other side, you should expect it to be extremely steep, almost vertical, and x to the negative 5. And you'll understand what I mean by extremely flat. I say this left side here is extremely flat. This right side is increasing very rapidly to a point it's almost vertical. We say in this case that the x-axis is a horizontal asymptote or we can say that the curve is approaching the x-axis asymptotically. Let's do that number 14. Let me write it down. Now, remembering correctly, was it y equals x to the, 5 to the negative x? Y equals 5 to the negative x. Power. If you remember the generalization that one side is real steep and that one side is real flat, you can probably get by just using 3 points. Plug in 1, 0, and negative 1. That should be sufficient. Let's try that. If it isn't sufficient, if you can't tell what's happening, then we'll plug in other numbers. But I bet you when we plug in 1, 0, and negative 1, I bet you'll see a pattern there. Plugging in 1, we get 5 to the negative 1 power. What's 5 to the negative 1? Don't say negative 5. Remember that definition of negative exponent. 5 to the negative 1. 1 over 5. I agree. That negative is going to make a 1 over, and then you have a 5 to the first power, which is just 5. Just like right here, 6 to the negative 1 became 1 over 6. 5 to the negative 1 became 1 over 5. Plug in 0. What's that going to give you?
1.
5 to the 0 power is defined to be 1. I agree. Now plug in -1. Watch out. You're going to have 5 to the negative. Now you're plugging in a -1. Okay, that becomes, that double negative becomes 5 to the +1, which is a +5.
Wait, why is there 2 negatives?
Because you have the negative from the function, and you're plugging in that negative there. You have 5. Okay, Amy, watch what I'm going to do. You have 5 to the negative, and then you plug in the blue -1. Negative becomes positive. 5 to the first power is 5. I think that those 3 ordered pairs are all we need. I'm going to write them out. 1, 1/5, 0, 1, and -1, 5. So let's draw our XY grid. Oh, I got this. Get rid of that. So write 1 up 1/5. So imagine breaking this little interval, that first interval there. Imagine breaking it into 5 equal units. You go right 1 and you just barely move up a little bit. I think I'll make it a red dot to stand out there. Then left, right, 0, up 1. The y-intercept right there at 1. Then finally left 1, up 5. So there's -1, go up 5, 1, 2, 3, 4, 5. From those 3 points, can you tell which side is going to be real steep and which side's going to be real flat? Which side's going to be the flat side, the left side or the right side? The right side. That's the side that's close to the x-axis. Remember, the graph can't go underneath it because a positive number to any power will always be positive. It'll be greater than 0. It won't equal 0. It won't be negative. So that means the left side's the real steep side. This is an example of exponential decay. Here you start out with a lot of whatever it is, and it starts decaying slowly, but there'll never be a time when there's 0 of that product left. Radioactive decay, think about that Chernobyl reactor. Even if that thing stopped producing radiation, and it hasn't, but if it did, the radiation that was produced would never completely disintegrate. It will never completely decay. You can wait and wait until there's not that much radioactivity in the air that it doesn't harm humans, but there'll always be some radiation there. And it'll take hundreds of thousands of years for that stuff to decay. Right? It's not going to decay. It's my understanding that reactor is still producing the radioactivity. They enclosed it in one of those concrete bunker domes, am I remembering correctly? It's been enclosed in one of those, and it's supposed to last 100 years before it gives way and the radiation escapes. Y'all believe that? Where'd they get that 100 years from? I'm going to tell you a secret. I remember in 1979 and 1980 when they were building those space shuttles, okay? They said each space shuttle is safe for 100 missions. And I remember How do they know? Where do they get this 100 missions and stuff? Well, we saw what happened there. I remember the day that it blew up, you know, and a lot of it over Texas, a lot over East Texas, my hometown. A lot of the stuff landing on our property up there. So, anyway, enough downbeat thoughts. Let's think on the good stuff. Is it A? Say no. B? Definitely not. I think I can just do it like, let's see. C? Yeah, I think that's it. If we look at D, we'll see it's going the opposite direction. So, remember, one side is nearly flat, almost horizontal. The other side is extremely steep, almost vertical. If you don't remember those generalizations, just plug in enough x values and create ordered pairs until you see the pattern, okay, until you see the shape. Any questions there? Exponential equations. An exponential equation, just like an exponential function, is a function where the variable is in an exponent. An exponential equation is an equation where the variable is in the exponent. Equation with variable or variables, I'll put a parenthesis S, equation with variable or variables in the exponent. There are two generally accepted methods of solving exponential equations. One of them requires logarithms. The other one, well, we can't use the one with logarithms yet because we haven't discussed logarithms. We'll do that. We'll start that in the next homework assignment. But what we can do is use something called the same base method. The same base method says that if b to the x is equal to b to the n, then x must equal n. When you see an example in a moment, the statement will seem obvious. When you see a real basic example, I'm going to make up a basic example right now. I think y'all can help me solve this equation. 5 to the x is equal to 5 squared. This is a very basic equation that uses the same base method. What's the only number you could put there for x to make the left side equal the right side? 2. If the bases are equal, then the powers have to be equal. You can drop the base and set the exponents equal. The problem is that they're not going to be giving you problems like this where the same base already appears and you can just drop it, okay? You're going to have to use what you know about exponents to get the same base on both sides. To illustrate this, we'll do number 16 and then we'll go back to number 15. Let me write the problem down. 2 to the 2x minus 7, 2 to the 2x minus 7 is equal to 16. I claim we have two bases in this problem. We have the base 2 on the left side, and we have the base 16 on the right side. Well, you say there's no power. Sure there is. If you don't see an exponent, just assume an exponent of 1. Our two bases are 2 and 16. 2 is a prime number. You're not going to change 2. You're not going to write 2 as a power of anything other than 2. That means if we're going to get the same base on both sides, we better be able to write this 16 as 2 to the power. So we have 2 to the 2x minus 7 on the left. How can we write 16 as 2 to the power? We have to be able to do it. Otherwise, the same base method doesn't work. 2 to what power will give us 16? We know 2 squared is 4. 2 cubed is 8. I think I heard Ernestina say 2 to the 4th power, and I agree. 2 to the 4th power. I have a cousin with your last name that, and that's why I was, did I just call you Angelina again? Did I? Oh, did I? I'm sorry, it's Ernestina. I'm just Abigail. Abigail, who's Ernestina? Oh my God, this makes it even funnier and even more tragic. So I was calling the wrong person. Did I email you correctly? Yes. Oh my God, okay. I just never see the people over there. But I have a cousin with your last name, and that's where I got Angelina from. So, yeah. And so, well, I'm waiting for Abigail to tell me. Then she told me a moment ago what that exponent was going to be. 4. I agree. Okay. You say, well, let's finish this problem, then we're going to discuss a what-if situation. Once we have the same base on both sides, set the exponents equal, and really getting the common base is the hard part here. Or in this case, it wasn't that hard, but that'll be the more involved part for the messier problems. Because once you have the common base, you drop the base, set the exponents equal. The thing you have here, you know how to solve this. What am I going to do first? I can't hear you. I agree to give us 2x equals. I'm waiting. 11. And then, okay, to give us x equals 11 over 2. For my final answer. You are going to have to use what you know about exponents to get the same base on both sides. Well, you say to yourself, suppose you can't do that. Suppose, don't write this down. Suppose we had 3 to the 2x minus 7 is equal to 16. The same base method can't, let me move this calculator. The same base method doesn't always work. If it works, then that's my preferred method. But sometimes it's just not possible to get a common base. We know 3 squared. 3 is a prime number. You're not going to change 3, so you better get 3 to the power here. 3 squared is 9. What about 3 cubed? 3 times 3 times 3, that's 27. You just skipped right over 16. 3 to what equals 16? You can't do it. In that event, if you can't get a common base on both sides, you'll use logarithms. And we'll see that in this method in the upcoming weeks. But I'm telling you this because for these problems here in this homework assignment, you must be able to get a common base. So keep that in mind. You may have to change both sides. We'll see some where you have to change both sides. But you have to be able to get a common base. Did I type in the answer? Did I type in? No, I didn't. 11 halves. Let's go back to number 15. There's something before we look at number 15. There's something called the power rule of exponents that you're going to use a lot as we go through this assignment and the assignment over the assignments over logarithms. The power rule of exponents. I keep saying the power rule of logarithms. The power rule of exponents. The power rule of exponents says if you have a base, let's say b, raised to a power, and that in turn is raised to another power. You have a power raised to a power. To write that as a single power of b, what do you do to the m and n? You have a b. What are you going to do to the m and n? Does anyone remember? Power raised to power, you multiply. M times n. Add that to your bag of tricks for when you run into powers raised to powers, and it will be happening. It's about to happen on number 15. The fact that I have this little bit of room here should make you a little more optimistic. It can't be that long if I can get it done in such a small amount of space. So 81 to the x is equal to 3. (81 to the x is equal to 3. What are my two bases? 81 and 3. You say, well, I don't see an exponent on that 3. I'll let you know there's one, 3 to the first. I generally start with the smaller base. Like up here, I started with the 2. Here, I'm going to start with 3. 3 is a prime number. You're not going to change 3. So you bet if you're going to use this method, you better be able to write 81 as 3 to a power. So move this up a little more. The x is on the outside. 3 to what power will give you 81? 3 to what power will give you 81? If you're unsure, just play around with your calculator. Well, 2 to the fourth, let's see, not 2. 3, well, 3 squared is 9, we know that. 3 cubed is 27. Another 3, 3 to the fourth, I agree, is 81. 3 to the fourth. So we've got a base of 3 on both sides, but we have a power raised to a power. What are we going to have to do? When you have a power raised to a power, you multiply, so you have 3. 4 times x is 4x, so 3 to the 4x is equal to 3 to the 1. We now have the same base on both sides. So using the same base method, we can drop the base, set the powers equal. We can drop the 3's, set 4x equal to 1. As I said, once you get the common base on both sides, the resulting equation isn't bad. There's only one step left. Divide by 4 to give you x equals 1/4. Any questions? Now we know what a 1/4 exponent is. That's a 4th root. So we're saying the 4th root of 81 is 3? Yeah, I agree with that because 3 to the 4th is 81. We've already done 16. How about 17? Three to the 2x minus 7 is equal to 81. This is similar to number 16. What do you think I'm going to try to use as my common base? 3 is a prime number. You're not going to change 3, so you better be able to get 3 over here. That has to be the common base that we want. So I'm just going to recopy the left side. 3 to what power equals 81? I think we just saw that. 3 to the 4th power. Now what can we do? Okay, so you're dropping the bases. You're setting 2x minus 7 equal to 4. Drop the base, set the exponents equal. This looks familiar. So that gives us 2x equals 11. So x is equal to... Didn't we get the same answer somewhere else? Number 16, well, it's just a coincidence. (18) and 19 involves something called the natural exponential, and before I look at that, there's another one I want to do, number 20. So we'll go back to 18 and 19 in a moment. (81) to the 3x 3x minus, is that an 8? That's a 6. Is equal to 729 to the x plus 3. (81) to the 3x minus 6 is equal to 729 to the x plus 3. Generally, I start with the smaller base and try to create the larger base. So our two bases are 81 and 729. Let's see, if we're working with 81, we know 81 to the first power is 81. What about 81 squared? Is that going to give us 729? No, it's going to give us something way far off. Over 6,000. So we've skipped over 729. That's a problem. Sometimes you have to change both sides. Sometimes you just have to change both sides. There's no way around it. We know we have to be able to get a common base because there's no other way to solve the problem. Well, 81, it seems to me I've been seeing a lot of 81 today. What were we using? 3 to the 4th? 3 to the 4th is 81. Let's see about 729. Can we get 3 to some power to equal 729? What's 3 to the 5th? Okay, 3 to the 6th. I think it's 3 to the 6th power. 3 to the 6th is 729. So we have, so we're going to have a 3 to the 4th and a 3 to the 6th. We just played around with our calculators, remembering 3 to the 4th popped up several times today and it was 81, so that's how I went to 3 to the 4th immediately. Otherwise, I would have tried 9, and I'll tell you something, 9 would also work as a common base, and to get the same question, same answer. 9 squared is 81. Look at 9 cubed. 729. So we could have used a 9. We'd still get the same answer at the end. We have a power raised to a power. What do we do when we have powers raised to powers? We multiply. So we're going to have to take the 4 and multiply it by 3x minus 6. What are we going to have to do? It's not just going to be a 12x minus 6. To multiply 4 by 3x minus 6, we'll need to distribute the 4. That's going to give me a 12x minus 24. You tell me what we're going to have here. I agree with 6x plus 18. Distributing the 6, we get a 6x plus 18. Now what can we do? Drop the base, set the exponents equal. 12x minus 24 is equal to 6x plus 18. And as I've said, once you get the equation, the common base on both sides, the resulting equation isn't that hard to solve. I move that 6x over to the left by doing what? 12x minus 6x gives me a 6x. What would I do with that minus 24? Add it. 18 plus 24 is giving me a positive 42. And then what? Divide by 6 to give us x equals 7. For my final answer. Now I'm going to make a classic new teacher mistake. New teachers have a tendency to rework the same problem different ways, thinking that's helping students, and it never does. And so I try not to do that. But in this case, I'm going to, just to show you that you'll still get the same final answer. If I were you, I wouldn't even write down what I'm about to do. 81 to the 3x minus 6 is equal to 729 to the x plus 3. Oh, let me switch. Oh, I did it check, did I? Did I check? Yeah, I guess I did. I said that we could have used 9. 81 is the same thing as 9 squared to the 3x minus 6. 729 is 9 cubed. So we have a 9. Distribute the 2 over the 3x minus 6 to give us 6x minus, wait a minute, it's 2, not 9. 2 times 3 is 6x. 2 times 6 is 12 equals 9 to the, distribute the 3. What's that going to give us? Now we have the same base on both sides, no parentheses at all. We can just drop the 9s and we get 6x minus 12 is equal to 3x plus 9. Subtract 3x. 6x minus 3x gives us 3x. Add the 12. 9 plus 12 gives us 21. What's that going to give us for x? What's that going to give us for x? 21 divided by 3. I agree with 7. Once again, we get the same answer, whether you use the base of 3 or the base of 9. So for those rare problems where there's 2 possible common bases, it doesn't matter which one you use. Any questions there? The natural exponential. Do you remember what an irrational number is, first of all? A rational number is any number that can be expressed as a fraction, one integer over another integer. An irrational number, well, it can't be written as an integer over an integer. It is a non-repeating, non-terminating decimal. When I heard that definition years and years ago, I thought that's ridiculous, because if it's not going to terminate, it's going to have to repeat digits. We only have 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we only have 10 digits. So when I say non-repeating, I mean it doesn't repeat the same block of digits over and over. A 0.3333 repeating, that's a 1/3. But it's a non-repeating, it doesn't repeat, there's no pattern to it. The digits appear just almost randomly. Non-terminating, it never ends. If these numbers never end, we need a way of expressing them. So we have to use symbols. What's the most famous irrational number? Pi. That ratio of the circumference of a circle to its diameter. It turns out we've been working with irrational numbers all semester long whenever we ran into a square root that's not a perfect square. Something like a square root of 2, that's irrational. Square root of 3, that's irrational. What about square root of 4? Is that irrational? No, because it reduces to a 2. But square root of 5, those are examples of irrational numbers. Notice the way we're using symbols. There's a new irrational number that I need to mention here. It's called the natural exponential. The natural exponential is denoted using a lowercase letter e, and it's approximately 2.718. 182818, and then it changes. For a moment it looks like it's going to repeat the same block of digits over and over, but eventually the digits start appearing randomly. Let's see, let me find that e. There it is. It's a cofunction of the natural logarithm. E to the first power, 2.718281828. Well, it doesn't show that then the digits start changing. It's not repeating. The approximation isn't really that important for us, okay? What you have to remember is that E is irrational. You can't write E as a power of anything other than E. So if you have an E as a base on one side and you want to get a common base, you better have an E on the other side as well. To illustrate, go back to number 18. Let me write this down. This is number 18. E to the 13x minus 1 is equal to e to the 11th all raised to the x power. What do y'all think I'm going to use as a common base? If I have an e on one side and I'm going to use a common base, I better have an e on the other side, and I do. Well, we have a power raised to a power. We know what to do there. What do we do when we have a power raised to a power? Multiply (11 times x is 11x. Now what do? Drop the base, set the exponents equal. So 13x minus 1 is equal to 11x. I think I'll subtract 11x from both sides to get a 2x here. What do you think I'm going to do with that minus 1? Add it over to give us a positive 1, and then divide by 2 to give us x equals 1/2. If you're going to solve an equation involving natural exponentials using the same base method, you must have e as the common base on both sides. Let's see, 1/2 Oh, this looks real similar. Okay. E to the 11x minus 1 is equal to e to the, let's say 9, all raised to the x power. What am I going to do here? This is real similar to number 18. Multiply the 9 and the x to give us, so we have e to the 9x on the right side. Oh, thanks. Oh, goodness. So that's a 9x. And then once we have the same base on both sides, no exponents, we drop the base, set the exponents equal. I think we're going to get another 1/2, aren't we? Subtract 9x, that gives me 2x equals, move the 1 over, And sure enough, we get another 1/2 as our answer. Any questions there? Well, let's see, 1/2. There's another E problem, number 21. Now, if this thing comes out being 1/2, I'm going to find it. I'm going to call shenanigans. If this answer is 1/2 also, I think something's fishy then. 1 over e to the negative x is equal to 1 over e to the 6th, all raised to the x plus 1. What do y'all think we're going to have to use for our base? We could, but I'm just going to use an e. I just have a preference. I don't like the base to be a fraction. We could use 1 over e, and if you view an example, I bet you that's what they do. But I think it's worth our effort to try to stop the bases from being fractions. And it's a good chance for you to practice with your negative exponents. Let me rewrite. I'm rewriting it. There. There's a negative x. I just want to use e as the base. I want my base to be e, and e. You're going to have to remember how to rewrite things like 1 over e to the 6th using a negative exponent. Go back to those negative exponent statements. Okay, so we have 1 over e to the 6th. 1 over e to the 6th. We're going backwards. We can drop the 1 over and do what to that exponent 6? Make it a negative. So you'll have an e to the negative 6. Did you follow that logic? We drop the 1 over, make the exponent a negative number. Hey, I don't see an exponent here on this 1. So what do we assume is sitting right here? A 1. So we're going to drop the 1 over. What exponent are we going to have here? A negative 1. Good. Y'all follow my logic there. We don't see an exponent on that e, so we assume it's a 1. So we drop the 1 over, the exponent becomes a negative 1. Here we drop the 1 over, the 6 becomes a negative 6. And now we have powers raised to powers, which means we're going to have to do what? Negative 1 times negative x. This is going to work out very nicely just to x, a positive 1x. We have e to the negative 6 raised to the negative, to the x plus 1. So what do we have to do? To give us, we're distributing to give us a negative 6x, and what else? Minus 6. Good. And now what? Drop the base, set the exponents equal. So we have x equals negative 6x minus 6. I think I'll move this negative 6x over to the right by doing what? Adding 6x. So we have 1x plus 6x, what do I have right here? 7x is equal to negative 6. Divide by 7 to give us x equals negative 6 over 7. Any questions there? And 1 over e would have worked. You could have used a 1 over e, but then you would have had to pull out a 6. I think it just works better by not having a fraction as your base. Maybe that's just my own personal preference also, but I think it works out cleaner by using your negative exponent properties. It's good practice to use your negative exponent properties and then just have e as the base. So negative 6 over 7. Let's see, 22. 22. I'm just going to see if they were significantly different, if I should do a 23 first. But no, they're about the same. This is number 22. We have the square root of 2 to the x plus 1 power is equal to 8 to the x. As we move into our logarithms discussion, we're going to have a little trick that's in our bag of tricks. Whenever we run into a radical from here on out, you're going to want to rewrite it using an exponent. That's going to be our standard practice for dealing with logarithms. So when I see that square root of 2, I'm going to rewrite that. What exponent is the same as a square root? What exponent is the same as a square root? A 1/2. So you have 2 to the 1/2 power. That little square root right there is the same thing as an exponent of 1/2. So on the left side, I have a base of 2. Can I change 2? No, 2 is a prime number. If you have 2 as that base, you better be able to get a 2 over here. So let's see. We need to rewrite 8 as 2 to a power. 2 to what power gives us 8? 3, I agree. Now we have a power raised to a power. What are we going to have to do? Multiply, so we have 2. Let's distribute. 1/2 times x plus 1 is going to give me 1/2 x plus, I did it here the last one. 1/2 times x is 1/2 x. 1/2 times 1 is 1/2, yes. 1 times anything is anything, so 1 times 1/2 is 1/2. Were you saying that? I just didn't hear you. What are we going to do here? Power raised to a power. Okay, to give us 3 times x is 3x. Oh, I think my battery went off. My battery's dead, so we only have one more problem after this, so I'll just speak loudly. We now have the same base on both sides, so what will I do? Drop the base, set the exponents equal. I like this because we haven't solved any equations containing fractions today. I think we need to solve this equation by eliminating the denominators. What can I multiply through by to get rid of the fractions? 2. The only denominator appearing is 2. How many total terms do I have? 3. I have 1, 2, so I have 2 on the left, 1 on the right. I'm going to go through multiplying by 2. Multiply all 3 terms by 2. The first product, the 2's cancel, leaving me with what? Just an x plus, here, what's canceling? The 2's cancel, leaving me just a 1. What have we got on the right side? 3x times 2. 6x. Why don't we move this 1x to the right by doing what? Subtracting 5x. No, 6x minus 1x gives me 5x equals 1. And then divide by 5 to give me x equals 1/5. For my final answer, Tony always says these are the last problems, so they got to be the most difficult. Well, if not the most difficult, they're certainly the most involved.
When you move the 1 over?
Mm-hmm.
Oh, wait, you're not.
I didn't move the 1. I left the 1 where it was. I subtracted 1x. 6x minus 1x gave me the 5x.
Oh, just kidding.
Any other questions there? Number 23 is real similar, okay? We're going to do that one too. First of all, let's punch in 1 over 5, and yes. Number 23. We have the square root of 2 raised to the x plus 4 is equal to 16 to the x. From here on in, as we move through logarithms in the next few assignments, whenever we run into a radical, we're going to rewrite it using an exponent. How can I rewrite the square root of 2 using an exponent? 2 to the 1/2. So we have 2 to the 1/2. That means 2 is our base. We better be able to write 16 as a power of 2. Two to what power gives us 16? I saw Abigail punching on that calculator. Is that one of those little Casios? Yes. Don't you love those things?
I had another one, but I got one of these just because
For the money, it's mind-boggling. When I think back 40 years ago when I was in school, a calculator like that, my God. But I'm waiting for you to tell me 2 to what power. What did your trusty little calculator say for 16? 2, I think it's 2 to the 4. 2 to the 4. 2 cubed is 8. 2 to the 4th is 16. And then,
And then you drop the base.
well, before I drop the base, power to power, you drop the base once there's no parentheses remaining. Once there are no parentheses remaining, right here, that's when you drop the base. Once there are no parentheses, you drop the base. So what do we do to get rid of those parentheses? Power raised to power? Okay, so we're distributing the 1/2 times x plus 4. That's going to give us a 1/2 x plus 4 times 1/2 is 2. I agree. 4 over 2 reduces to 2. What about this one? 4x. And now I can drop the 2's, set the exponents equal. What do you think I'm going to do here? Okay, I'm going to multiply through by 2. How many times am I going to have to multiply by 2? I think we're going to, not only do we have to multiply the things that have x's by 2, but remember you're distributing, so you have to multiply this 2 here by 2 as well. Multiplying by 2, multiply each term by 2 to give us 1x plus here 2 times 2 is 4 equals 4 times 2 is, so, and then what do you think I'm going to do? I'm going to minus that 1x there. That'll decrease negatives. I can move the 8x over, but then I'd be picking up negatives. So I'd subtract the x. 8x minus 1x gives me 7x equals 4. And then divide by 7 to give us x equals 4 over 7 for my final answer. So 4 over 7. And that's it. There's no review problems here. This was all new material. Any questions? Did we do them all? Yep, we did. Okay. Any questions? I'll stop recording.